Hey guys, in this video I'm going to talk about torque. So we've learned that Newton's second law can be used to find the acceleration of objects if we know what forces are acting upon them. Well, Newton's second law is really only useful if the entire object by itself is moving as a whole. It's not really very useful if certain parts of the object are moving differently than other parts of the object. So for example, I have a heavy beam here. So this heavy beam is fixed to rotate about this point right here. So if I move this up and down, obviously the end of the beam is experiencing some kind of acceleration, but this point is not experiencing any acceleration at all. So Newton's second law, as we learned them so far, won't be very helpful in understanding what's going on with this beam, and so that's why we need the notion of torques. So there are several things about torque which are very intuitive. So the first one is that, okay, gravity wants to pull this beam downwards. I can stop that by applying a force right here, and I have a force sensor here so I can tell you how much I'm applying. I'm applying about 20 Newton to keep this beam stationary. Well, it turns out that if I apply that force at a different location, say a little bit closer to the pivot, that amount of force will be different. And in this case, it's about 29 newtons. If I apply that force further away, I get about 12 newton. So as I apply the force in different locations, the amount of force I have to apply changes. So that's the first thing about torque, is that it matters where you apply the force to keep the beam from rotating. Also, I applied those forces perpendicular to the beam. What if I apply the forces at a different angle? Well, so if I apply this force at a different angle at the same location, I get 30 newton. So it also depends on the angle at which you apply the forces. I can also do a much shallower angle. I get about 22 newton. So apparently, to keep this beam from rotating, it depends not only where I apply the force, but also the angle at which I apply the force. So it turns out that mathematically, the torque is the cross product of the position at which I apply the force relative to the point of rotation and the force itself.
So here's our definition of torque. In the context of that beam, there's the force that I was applying, where this is the fixed point. So that position vector is the position starting from the point of rotation out to where the force is acting. So you probably recall that this thing is called a cross product, and we have another way of writing the magnitude of a cross product. So the magnitude of a cross product is simply the magnitude of each vector times the sine of the angle between them, where we need to find the angle between them by putting them tail to tail. So they need to be oriented like that. In our case, we don't have our R and F oriented tail to tail, so we need to move the vectors around. What I'm going to do is I'm just going to move this R over here. That's the same vector at a different location, so the angle between them is phi, and that's what I can put in as that phi. Now that doesn't tell us anything about the direction of the torque, but we can use the right-hand rule to determine the direction of the torque. So recall the right-hand rule. First, you point your fingers in the direction of R with your right hand. Then you bend your fingers into the direction of F, and your thumb points in the direction of tau. So if I do that with this beam, point my fingers along R, curl my fingers up in the direction of F, my thumb is pointed out of the page. Normally that just determines a positive or negative direction. Of course, that might be the z direction if your xy plane is within the plane of the page, but normally that just defines a positive or negative direction, so we know if the torque being applied is positive or negative. So how are we going to use this fact to determine how torques keep things in static equilibrium? We're going to need to do a little bit more work. So recall that we can define the force as a change in momentum over a change in time. Actually, that's a statement of Newton's second law if you take only one force acting on an object. Well, I want to take this definition and put it into this force right there. So that means that the torque is now a cross product between the position vector and the change in momentum by change in time. Well, if I assume that the point of application of the force right there is not changing in time, then this thing is time independent, and I can pull the derivative through this like that. But now recall that R cross P, that's just the definition of the angular momentum. So we found that we can write a torque as a change in angular momentum. So this expression might look a little bit strange because this torque was due to just one force whereas this angular momentum is the angular momentum of the entire body. So maybe what we should write is something more like this, where those brackets indicate that this is the change in the angular momentum from one specific source, specifically from the source of that torque. We could even label it A if we wanted to just talk about the torque from that specific source. Well, if we want to talk about the change in angular momentum of the entire body as a whole, we'd have to talk about summing up all the little changes in angular momentum from each torque. But of course, that's just summing up all the torques on the body. So this equation right here is exactly like Newton's second law. It's the sum of something that's related to forces, getting you to the change in momentum. That's the exact same thing we have for Newton's second law, except over here we have forces, and on this side we have the change in linear momentum. Here we have a sum of torques and a change in the angular momentum. So this is what we need in order to study the static case as well, because in the static case, we have that the object is either not rotating or rotating at a constant velocity. And of course, if it's rotating at a constant velocity, that means that the angular momentum is constant. So the time derivative of the angular momentum is 0. And that from our previous equation shows us that the sum of the torques is 0. So the condition for rotational equilibrium is that the sum of the torques is 0. This is just like the case for translational equilibrium, in which the sum of the forces is equal to 0. So let's consider a relatively simple example of a massive hanging beam. So this is the beam. It has a length L. There are 2 ropes hanging from either side of the beam. And those 2 ropes have tensions T1 and T2 and angles with respect to the vertical of phi1 and phi2. And this is massive, so I also need to assume that the beam has some mass m. So what I want to do is I want to have a problem where I'm given the mass and length of the beam as well as this angle right here. And my unknowns are going to be T1, T2, and phi2. And in fact, those are the things that I want to find. So the easiest way to do torque problems is to make a diagram similar to a free body diagram where all your forces are coming from the center of mass, but I actually want to have the dimension of the object in there because these forces are no longer coming from just the center of mass. So that's what my free body diagram looks like in this case. Notice that it's essentially the same because I happen to have the tensions labeled there, but now I have the locations at which they act. And also I've included the force of gravity acting at the center of mass. Remember, that is where the force of gravity always acts, at the center of mass and straight downwards. So if this beam is in static equilibrium, that means that the sum of the torques has to be 0. And if I want to say find one of the tensions, then I can know they all have to balance out, not in a vertical horizontal sense, like in Newton's second law, but in a rotational sense. So the torques have to balance out. So how many torques do I have actually acting on the beam? Well, the number of torques has to be equal to the number of forces, because every force makes a torque when it acts at a distance r. So I should have 3 torques, one from T1, one from Fg, and one from T2. So there's my statement of rotational equilibrium, where I've just labeled the torque from this guy as tau1, the torque from this guy as tau2, and the torque from gravity as tau g. So now before applying this equation, because there's an r right here, I need to set a coordinate system. In this case, that basically means pick an origin. So I'm going to pick the origin of my coordinate system to be right here where T2 is acting. Now, I didn't actually say that this thing was rotating about any given point, unlike the beam. The beam that I had set up in my office had a point right there where the beam was stuck. So that would be the natural point about which to calculate torques. Here we don't necessarily know, but let's just pick a nice point, and I'm going to pick that point. Why do I pick that point? Because the torque now, due to the tension T2, it should be the distance from my reference point to T2, but the distance from my reference point to T2 is 0. So now I have that the torque due to the second tension is 0, and that's going to make my problem significantly simpler. I didn't have to pick that. I could have picked something else. I could have picked, for instance, T1 and then made the torque from T1 be 0. Or I could have picked the point there and said that the torque due to gravity is 0. But actually, because I didn't know T1 or T2, if I picked that to be 0, then I would not be able to solve the problem. In fact, if I had picked here to be 0, then I would have 2 unknowns, T2 and phi 2. So actually this is the only point I can pick that will allow me to solve this problem. So now the sum of my torques is tau 1 plus tau g. This is writing out the torque equation. Remember that the two forces times the sine of the angle between them. And I'm just calling these two angles some arbitrary angle I don't know what they are. I'm also calling these radii some arbitrary radii I don't know what they are. Let's first find out what the radii are. Well, this thing needs to be from the reference point to t1. So then that, in this case, that's from here to there. That's the length L, so that thing is L. This RG should be the distance from the rotation point to where gravity is acting. Gravity always acts at the center of mass. That's at the center of the beam. So that's L over 2. So now we need to deal with the angles. So recall that the angle needs to be the angle between R and T, where R and T are tail to tail. So let me draw a picture of R1, which is right there, and you can see that it is not oriented tail to tail with respect to that vector. So I'm going to take R1 and move it right there, where I get that, and that is now the angle that I need to put in there. But you notice now that that angle right here is actually 90 minus phi 1. So that's what needs to go in for theta 1. I'm going to play the same game with the angle due to gravity. That's my distance between the reference point and where gravity is acting. I can move that over simply by putting it right there. And then it's pretty clear that the angle right there is 90 degrees. Sine of 90 degrees is 1. So finally, when I wrote this expression, I didn't think too much about the signs here. So we need to check with the right-hand rule to determine if those signs are correct. Well, let's look at T1. If I go in the direction of R, curl into T1, I get out of the board right there. So let's just call that positive. But for the gravitational torque, I go this way to curl in the direction of FG. I need to turn my hand around, and so my thumb now points into the page in the negative direction. So I really should have made this guy, that should be a negative sign. And because they're all, the sum of the torques is going to be equal to 0 because this thing is static, I sum them up to 0. But now if I look at this expression, I know everything in here except for t. I know what L is, I know what Fg is, it's just m times g. I know this angle is 90 minus phi 1, which is one of my knowns. So I can now just solve this for t1, so I'll do that real quick. And I find that the tension is mg divided by 2 sine 90 minus phi 1. That is, it is independent of the length of the beam. Okay, so that's how you use rotational equilibrium and the sum of the torques to find one of the tensions acting on this beam. To find the other things, which is T2 and phi 2, we've already used the condition of rotational equilibrium, which is only one equation. We're going to need some more equations. So we're going to have to go back and use Newton's second law for translational motion, because this thing is also not translating. So I'll do that real quick, but I just wanted to point out that we're no longer going to be doing rotational motion. Now we're going to go back, now that we know this tension, we're going to go back to using Newton's second law in the XY translational sense. So here's my free body diagram. I'm going to pick a coordinate system, and I'm going to write down Newton's second law. I have 3 forces here, but 2 of them, T1 and T2, are going to be in both the x and y directions. So I'm going to break those up into x and y components. And I'm going to write those x and y components in terms of the angles. And of course, this is all going to be equal to 0 because this thing is in rotational equilibrium. So we better check our equations to see that we have the right number of knowns and unknowns. We know that we now know what T1 is from the previous slide. We don't know what T2 is, we don't know what phi 2 is, but there are 2 unknowns right there. So we're going to use these 2 equations to solve for those 2 unknowns. So I'm first going to solve the first equation for T2 and plug it into the second, so that's just a simple rearrangement. Dividing by sine phi 2, and then I'm going to plug that in right there. And now this particular combination of angles, those are the only place that I see phi 2. Cosine divided by sine is a cotangent. Now do a little rearrangement to solve for the cotangent. And that's what we get. Now, to make more progress, let's assign some numbers to these things. Let's take phi 1 as 30 degrees, and if I go back a couple slides and plug that phi 1 in, along with a mass of, say, 50 kilograms, I get a tension of about 283 Newton. So now if I take that T1, plug it into this expression, I can find what this angle is. And it turns out that phi 2 is about 30 degrees. Now that totally makes sense. I mean, think about what I have here. I have a symmetric situation, which is a beam which is hanging flat, and a tension here and a tension here. Those two tensions have to be the same. Those two angles have to be the same. So what we should be able to do is check, put this guy back into here, and check to make sure T2 is the same as T1. And that's indeed what we get. That didn't have to be the case, right? I could have made the beam at an angle, and then the problem would be different because FG would be right here, but FG would have a different angle than 90 with respect to the beam right there, and so this term up here, right here, this would have an additional angle in it, and those two tensions wouldn't be the same.
Alright, so let's review how to solve a torque problem. Start with the free body diagram, but make sure that you have forces acting at the actual locations on the object, not at the center of mass, because torque requires you to know how far away from a point a force is acting, so you need to have that in your diagram. Then you write down the condition for rotational equilibrium, which is the sum of the torques being 0. That's the physics that we're going to use to figure out how big the torques and the forces are in the problem. Then you use the definition of torque, the position of a force times the force itself times sine of the angle between those two vectors. That's the major challenge in these problems, is writing down the torque due to each force. Remember, the R and F, they need to be placed tail to tail in order to figure out what that angle is. So that means you might need to move one or both of them around to make sure that you can figure out what that angle is. Remember to put in the right negative signs. Some torques cause objects to rotate counterclockwise. Some torques cause objects to rotate clockwise, and those need to have different signs. So you can use the right-hand rule to get that, or you can just say, I see this force is making this object rotate clockwise versus counterclockwise, and put in the negative signs by hand. Then you should be able to do a solution. You only have one torque equation, so you should have only one unknown, and you should know everything else in order to do the solution. All right, great. Thanks very much. I know torque can be a complicated topic, so I hope this video has helped you a little bit, and you'll be more successful in solving these problems in the future. Great. Thank you. I will see you guys in class.